Hello, and welcome to Easy as Pie with Mr. Carpenter. I'm Mr. Carpenter, and today we'll talk about the dreaded partition, which is one that last year's geometry students did not take a liking to, but I feel can be described in a way that it makes it a lot more bearable, especially honor regions. So with the partition, we're talking about ratios, and if you weren't here in class, I used this idea of a chocolate bar, which I will make a red chocolate bar because I'm lazy and I don't feel like changing the colors. So the idea is that I'm holding the chocolate bar on this side and you are holding the chocolate bar on the other side. And I ask you to break off the chocolate bar so that the ratio of your chocolate to my chocolate is 3-1. So how would you break that chocolate bar? So the ratio of your chocolate to my chocolate is 3-1. Now, if you decide to break the chocolate bar there, then you would be right? And we come to this conclusion naturally, right? Because for us, a 3-1 ratio means for every 3 pieces that you get, I get 1 piece. That's how ratios work. So when we think of a 3-1 ratio, we're really trying to split the chocolate bar into 4 equal pieces and make it that you get 3 of those pieces and that I get 1. And thankfully for us, the chocolate bar is already got these pre-built ridges inside of it that already splits it up into 4 equal pieces. So all we have to do is to pick the ridge to break off that makes it so that we get 3 pieces and that I only get 1 piece. That's what makes the partition so easy with the chocolate bar. Because 1, it's measurable, right? Its pieces are all measurable, and they're already pre-built ridges, which split up into perfect pieces. If I were to make this something like a 5-7 ratio, now it becomes a little more difficult, right? Because 5-7 means that we would ideally want to split this up into 12 equal pieces, right? And make sure that you got 7 of those pieces and then I got 5. But this chocolate bar is not split into 12 equal pieces, right? We would have to do that heavy work on our own by measuring it. So I use all this to kind of segue us into our partition that would be more acceptable on a geometry level, which would be on a line segment, right? And we're going to start with a horizontal one and see how this translates into other partitions, right? We're going to place point X so that the ratio of AX to XB is 3-1, right? So we have this point X, and we're going to take that point and put it somewhere on this line. Now, where exactly, we're not sure yet, but we're going to place it so that the ratio of AX to XB is 3-1. Now, as you saw with the chocolate bar, we were able to partition 3-1 so easily because the chocolate bar was already ridged into 4 equal pieces. So if we want a 3-1 ratio, that means ideally we want 4 equal pieces. And since this is a measurable line segment that's horizontal, which means I can count the boxes, I can do this quite easily, right? I have 1, 2, 3, 4, 5, 6, 7. I have 8 altogether. So if it's an 8, if it has a distance of 8, I want to split up into 4 equal pieces. 8 divided by 4 would be 2. So I could create the ridges in the line segment myself, right? And now I've kind of made my chocolate bar that has 4 equal pieces. And AX would get 3 of those pieces. So where do you think AX is going to go? Well, it should go right here. If AX goes there, then look, AX gets 3 of the pieces, and XB gets 1 of the pieces. And we have successfully partitioned this line segment. So now that we've taken care of this, we can move on to an example where it's a diagonal line. And the thing with a diagonal line is we can't exactly partition it the same way we partition a horizontal line because we can't count boxes on the diagonal like we would a horizontal line, right? That's not how the coordinate grid works. It only really counts well when we're talking about verticals and horizontals. But partitioning a horizontal line is much easier for us. So it'd be really cool if we were able to have a horizontal line available for us to partition that could translate to the diagonal. And the thing is, we do. If we draw this right triangle, and this is our strategy, if we draw this right triangle connecting the vertices, right, now we have a horizontal line to partition. This line right here. We want to plot point W that partitions QR in a 3-to-1 ratio, which means that the ratio of QW to WR is 3-to-1. So once again, if it's a 3-to-1 ratio, that means I want 4 equal pieces. And this line segment is 1, 2, 3, 4, 5, 6. This one's also 8 pieces. Great, so if I have a line segment of 8, I want to cut up into 4 equal pieces, then each piece would be 2 boxes long, because 8 divided by 4 is 2. So we put a ridge there, and a ridge there, and a ridge there. So where would I place point W? Well, ideally, I'd want to place it right here. Right? Because we're thinking about R as kind of like this line segment at this point. And now QW gets 3 of the pieces, and WR gets 1 of the pieces. So how does this translate to the diagonal line, though? Well, believe it or not, if you take this point, and from there you draw a perpendicular line, which is very easy to do because you are on the coordinate grid, and place the point where it intersects the diagonal, this point 2 will also partition the diagonal in the same way that it partitioned the horizontal line. And that's due to something called the side splitter theorem, and that is something you'll learn in the future, right? So we will prove that this works in the future, but for now, all you have to do is understand that it works. If you partition this line and then draw a perpendicular, it will also partition the diagonal just as well. So that is all for Easy as Pie with Mr. Carpenter. Thank you so much for watching, and I will see you in the next video.